The physics of the 20th century yielded two of the most important and successful descriptions of the behavior of the universe ever to emerge in science since Newton. The first of these theories is Einstein's general theory of relativity, which ultimately describes how gravity works in the universe above and beyond that of Isaac Newton. Because by the 19th century, it had become clear that there were discrepancies in Newton's understanding of gravity. It wasn't wrong, we still use Newton all the time, rather his understanding was incomplete. One interesting thing about Newton's theory is that he described gravity, but specifically wrote that as to what gravity actually is, he would feign no hypothesis. General relativity just describes gravity bending space-time, but we also know that general relativity is also incomplete, because it also does not tell us what gravity is. It just describes how it behaves on the scale of the big in the universe. It does not address gravity in the world of the small, and that led Einstein to spend the last 30 years of his career trying to come up with a quantum theory of gravity to no avail. The other theory, however, specifically describes the world of the small, quantum theory, a description of the behavior of the universe on the smallest scales. The ethereal quantum world lurking below the atom. But there are problems. While general relativity works almost perfectly on large scales and is well tested and proven, there are instances like black hole singularities where it just starts spitting out infinities. It simply stops working, illustrating that it is incomplete. In the quantum realm, general relativity specifically requires a quantum theory of gravity. That is also needed for the singularities to really understand what happened with the Big Bang and what's going on inside black holes. This has led to continuing Einstein's search for a quantum theory of gravity that would integrate gravity into the regime of the quantum. The big problem is that gravity is incredibly weak on quantum scales. Take a small magnet. If you stick a magnet to a refrigerator, it is able to stay there indefinitely, despite the gravity of the entire planet tugging on it. Electromagnetism is much more powerful, as are the other forces, than gravity is. But classically, it's always made sense to view gravity as a force, just an incredibly weak one. But it has huge implications on the universe nonetheless, as gravity is the glue holding everything together. But that leads to a further mystery. Gravity is linked to mass, of course, but we see more gravity in the universe than we should see, way more, in relation to the mass that we can see. This led to the hypothesis of dark matter, where some non-interactive particle accounts for the additional gravity without interacting in any other obvious way. Dark matter makes up over 5 times as much matter in the universe as our normal matter does, yet it can pass seamlessly through walls and even you. You have ghostly dark matter passing through you, along with neutrinos, constantly. This gets tricky in that there's very little else to go on regarding dark matter other than gravity and what it actually is. The discrepancy is not a very evident phenomenon on the scale of the solar system, yet on large scales, such as galaxies and galaxy clusters, it becomes readily evident, and indeed is also seen with gravitational lensing on those scales, and even the structure of the cosmic microwave background radiation left over from the Big Bang. But without those huge scales, it's possible we might have never known dark matter exists, even in the far future of science. But an oddity here is that while quantum theory does scale up into the world of the large, quantum effects tend to get lost in the noise, and the behavior of that noise switches over to general relativity, yet gravity, if it is a quantum field, remains very evident and really rules the world of the big. Regardless, there is either missing mass here, the simplest explanation, or there is something wrong with our description of gravity at large scales, something for which there is no other evidence, potentially indicating that. It also looks in every other way that our understanding of how gravity behaves is correct and universal. So invisible mass is the simplest answer for what we see, hence dark matter. The highly non-interactive neutrino shows us that such things are possible. But none of this tells you what gravity actually is. Once again, it just describes how it behaves. But there is another idea above and beyond it, being another weakly interacting massive particle like the neutrino. We know those exist, they are a kind of dark matter, so again the simplest answer is that there are other types of those particles. But one alternative is more complicated and may have in some ways even better legs. That dark matter could in fact be gravity itself. This gets back into gravity on the quantum scale. If gravity indeed is active on quantum scales as a force, which it should be, partly because all other known forces in the universe are quantum, it stands to reason that like all other forces of nature, it is conveyed by a force-carrying particle. Known as the graviton, this particle has never been detected, other than its collective large-scale gravitational effects, which starts sounding something like dark matter in a sense, but that gets worse, meaning that gravity itself could account for dark matter because it is, indeed, a particle. There are a few things that we do know about dark matter beyond its gravity that comes from observations. The first thing is that it moves slowly and does not propagate at the speed of light, even though gravity's effects do, which can be expressed as dark matter being cold. It also does not like to interact with itself. It's limited on what it can do there as far as colliding with itself. We also know that it clumps. And finally is that it's non-interactive with regular matter or photons, which is where the term dark comes from. We also know that dark matter can't be any of the particles we've confirmed to exist in the quantum realm. We also know that dark matter particles can't be electrically charged, and that they must be stable, and that dark matter can't be the neutrino, despite neutrinos famously being very weakly interacting, making them hard to detect. They just aren't heavy enough or numerous enough to account for it. At best, they could only account for probably less than a single percent of what we see as far as excess gravity. Most popular theories of dark matter hypothesize either a weakly interactive massive particle or an axion, which is another hypothetical particle, but an interesting one. And it's both a possibility for cold dark matter, but also solves a completely different problem in particle physics. The strong CP problem, which is a vexing major mystery in physics, but that's for another video. But in this viewpoint, it's the graviton particle itself that is dark matter. There are some good reasons to consider the graviton as dark matter. First is that there is no real reason that graviton would be massless, even though it's envisioned as such. But it may not be. That's still an open possibility. There are only constraints on just how massive it can be. There is an upper limit, and it's very small. The net effect of this is that gravitons may be able to clump, just like dark matter seems to. Get enough of them in the universe, and they could, in principle, account for dark matter. Second is that the graviton, even though it's still undetected, isn't all that hotly debated in science because gravity seems very likely to be quantum in nature, which means the graviton exists. The other options are more speculative in actual fact, and it may actually be significantly less messy. Take the axion. For it to be the culprit, you have to add in a new field in nature. If a particle, it could involve a supersymmetric particle, but the problem is, there is significant evidence that supersymmetry does not exist. If it's a Kaluza-Klein particle, it requires extra dimensions, and there is no evidence for that. Last is a sterile neutrino, which requires one to invent new physics, even though observational evidence does not support this. After all of that, the graviton starts looking rather attractive because it has a lot less baggage. All you need here is for gravity to be quantum, and that in itself means the graviton must exist. Another point in favor of the graviton being dark matter is that models of them, if correct, predict that it will be collisionless, like dark matter is. This is actually a huge issue because that also makes gravitons exceedingly difficult to detect. Maybe it might even be practically impossible. There have been studies that have shown that even a gas giant around a neutron star would only ever see a graviton interaction, other than gravity, once a decade. Dark matter may or may not be that bad, but we do know that collisions should be very rare, and might be why we haven't seen a particle of dark matter yet. This actually has an interesting implication in that gravitational waves that we see from things like black hole mergers are gravitons, meaning that gravitational waves were a phenomenon of dark matter the whole time, right under our collective noses. But there are arguments against this idea of gravitons as dark matter, and indeed the graviton's existence, of course. And part of it is the expansion of the universe and how particles tend to lose energy because of it, and the fact that the effect of gravity seems to travel at the speed of light, which massive particles can't really do. Yet if you were able to pluck the sun out of the solar system, Earth would not go flying off into space until the change made it to us at the speed of light. It's unclear how that would happen under a graviton theory of dark matter. But it has to be said, maybe, and it's certainly possible, that gravity isn't a force. It just superficially seems like one. And that it really is just a warp caused by mass in space-time, as general relativity describes it. The one thing we do know, however, is that the universe is not beholden to what we want it to be. Rather, it is what it is, and all we can do is try to understand it. But ultimately, we also know that there is much we don't know, and maybe there's a point where we reach the limit of what we can know. Thanks for listening. I'm futurist and science fiction author John Michael Godier, currently eyeing the general theory of relativity suspiciously. I don't think it can be debated. It's hiding something. Or something is hiding from it. Wonder where the machinations of quantum mechanics plays in here. And be sure to check out my books at your favorite online book retailer and subscribe to my channels for regular in-depth explorations into the interesting, weird, and unknown aspects of this amazing universe in which we live.